So let's get started with going over the multiple choice of this exam. Here we go, number one. Let's be crazy and go in order. So number one, okay, what they're talking about in terms of complete combustion of a sample of a hydrocarbon, what they're really talking about is combustion analysis. In combustion analysis, we take our hydrocarbon and with excess oxygen, we produce CO2 and water. Now, what you need to understand in this type of analysis, this type of empirical analysis, is that when we take our hydrocarbon of some number of carbons and some number of hydrogens, you need to understand that all of the carbon, okay, that was from the original hydrocarbon is now in the CO2, and all the hydrogen that is now in the water as a product of combustion came from the hydrocarbon as well. So if you can understand that all the carbon from the CO2 came from the hydrocarbon, all the hydrogen, we can work backwards to figure out this formula. Now in this case, they're not giving us any grams or mass, but what they are saying is there's equimolar quantities of carbon dioxide and water. So that's important as we go forward. So if we have equal molar, molar means how many number, okay, we need to figure this out. So what we need to do is see what would give us that scenario. So if you think about it, equimolar carbon dioxide, that means we have what? 1 carbon dioxide. And let's write 1 water. And I'm going to write that as a ratio. So by saying equimolar quantities, okay, I'm thinking we have equal amounts. So let's just make it 1 to 1 and see what we have here. Now when we do 1 to 1, what do we see? Well, we see that there is 1 carbon, right here, and there are 2 H's. So essentially, I'm looking at a basically 1 carbon to 2 H ratio in my formula that would give me equal amounts in my stoichiometric relationship, meaning when I take my hydrocarbon and break it apart, we should get the same amount of coefficients out here. So this has to be a 1 to 1 ratio. And of course, because there's 1 carbon to 2 H's in one of these and one of these, I'm looking for a formula that has a 1 to 2 ratio. And the only one there is choice C, where we have a 4 to 8. Now, Mason Zakrotsky, it's 4 to 8, but that reduces to 1 to 2. And when we're doing empirical type of analysis or analytical chemistry, oftentimes we're dealing with the lowest ratios in a laboratory. Okay, so the only choice there is a choice C there with a again 1 carbon to 2 ratios. All right, number 2. So in number 2, what we have here, we have some more organic compounds, and what they have is the equilibrium vapor pressure. Now people say, oh my gosh, vapor pressure, equilibrium, what do you mean? Well, you need to understand when we measure vapor pressure, we always do so in a closed system. So if I have a bottle that's open and I have some liquid, well, we can't really measure the vapor pressure because we have atmospheric pressure coming in, and 2, we have the pressure kind of the vapor pressure, which is nothing more than the liquid molecules escaping into the gas phase, creating a force upward. So if the bottle's open, then of course these molecules can escape and you don't really get a good value what the pressure really is. So what we do is we seal the container and we let the molecules evaporate at some known temperature or constant temperature, and we let them evaporate to the point where the rate of evaporation is equal to the rate of condensation. And so when we get that equilibrium, that's really where we measure vapor pressure. Again, with an open system, very difficult to do so. But when we close the system and allow it to have equilibrium, the rate of evaporation equals the rate of condensation, we can measure what saturated gas molecules or pressure due to the liquid molecules escaping. So it's important that you realize that's where they're coming from there. Now that being said, after that, all we're considering is the vapor pressure, which is the force of liquids escaping, okay, into a gas phase from the top of the liquid. That's all. We're at the top of a liquid, and what is that force in a closed system? Okay. Now, what we should know at this point from previous learning or chemistry courses, even the most simplest kind, the liquids that evaporate the easier have the weakest intermolecular forces, or IMFs. So why is that? Very simply, molecules that attract themselves, and just think of these little bean or whatever shapes you think these are, they're attracting themselves. If you're a liquid, it's because these molecules, these little round objects I'm drawing, are attracting themselves. And they could be hydrogen bonds, they could be dipolar forces, London dispersion forces, LDFs, could be all three as we've talked about before, but there's some kind of attractive force. Now, if this has a weak attractive force between the molecules, you could surely understand that these molecules would leave much easier. And that's what's happening here. So who has the weakest? The ones that evaporate the easiest. And if they evaporate the easiest, they are overcoming these weak attractive forces at the top of the liquid layer, creating the what? The greatest vapor pressure. So the liquid that has the highest vapor pressure or the highest force coming off of a liquid is the one that has, of course, the weakest attractions. The reason why they are a liquid is because the attractive forces between them, not bonds. So that's why choice C is the answer. Okay, weaker the attractive forces, higher the vapor pressure. Think of the liquid nitrogen. Think about this, nitrogen molecules. Okay, they are very nonpolar, so they have weak LDF forces. They don't have a lot of electrons and they're small, so they don't attract themselves very well, and that's why they boils at negative 196 degrees Celsius. Okay, let's move on to 3. So in this question, they're giving us at number 3 the ion charge and, of course, the ionic radius. And based on the data table above, which of the following correctly predicts the relative strength of attraction of these ions to water molecules? Now we know that water molecules have a negative side and a positive side, and they're bent and they're sp3 hybridized and all that good stuff. But the reason why these ions interact with this solvent is because water has some very good charges here for them to attract to and surround as molecule ion attractions. But that type of attraction is based on Coulomb's law. And Coulomb's law very simply is equal to the charges over the radius squared. It's an inverse square law. So what do we know from learning is that Coulomb's, which is the electrostatic attractive force that a positive or a partial positive would have with a negative. So that attractive force can be measured by Coulomb's law. And these are the size of the charges, and since they're all +2, we're kind of eliminating the difference in the charges. So now we're looking at the denominator here, the radius. And if you've got a bigger, radius, like barium, a bottom number in the denominator that's bigger is going to make the size of the Coulomb, or the electrostatic attraction, to be lower, okay? So what does that mean? Well, that means if I was to make my ionic radius really small like zinc, the smaller my radius, smaller the diameter, the bigger the electrostatic charge. And we've talked about this. If you've got a +2 in a smaller area, like a smaller radii of an ion, then I always say that that has a what? A very high charge density. There's a lot of positives here in a small place, and that's always speaking to coulombs. So zinc, is going to have the greatest amount of charge density or electrostatic attraction by Coulomb's law, however you want to talk about it. And calcium would be next because it's the second smallest, and therefore barium. So that's why A and B make sense. And they look at the answers here between these two, because the smaller ions have a stronger coulombic attraction or electrostatic attraction, and that's why A is the best choice. It's not about electronegativity, it's not about polarizable or less electric. It's just a bottom line is it's about this formula here. I say charge density, but you can say a greater coulombic attraction. All right, and it's based on this formula. So number 4. Number 4, zinc is used to reduce other compounds. What does that mean? Well, we know zinc, like a lot of metals, is 0. It's a solid, and it can't oxidize. I mean, it can't reduce. It can only lose electrons. Leo the lion says Gur, so losing electrons is oxidation. So zinc will lose 2 electrons like most metals do, or lose electrons in general, because they hold on to them loosely. Metals are bigger. And of course, zinc becomes that zinc plus 2. In fact, we've talked about why zinc becomes plus 2. It loses 2 electrons from its 4s. Any case. But its ability to reduce others, what are they talking about? That sounds a little confusing to me. Well, if zinc only oxidizes, that means it's what we've called a reducing agent. Think opposite, right? So if it's getting oxidized, likes to oxidize, what it can do is it can lose its electrons, but more importantly, it can force those electrons onto chemicals, okay, and help them reduce. So it's the idea that zinc is a reducer, okay? It helps reduce others by itself oxidizing. But if you didn't get all that, the bottom line is you can identify that zinc's a metal. It's used to do other things, and they're asking if a chemist needs a substance that is more effective in doing things like zinc does. In this case, its reducing ability. So we're looking for something else that will do this even more. Who else can push its electrons better onto other things? Which is the same thing as saying which one can oxidize better. Who is a more reactive species? And if you look at your choices, we have ions, and then we have a standalone metal. Hello, that's your answer. Now, you should know sodium, okay, is far over to the left on the periodic table. It's an alkali metal, and you should be aware that these guys are a little nasty because they love to react in water. So they are very explosive in water because what do? They push their electrons, okay, very aggressively onto water, okay, and they make the hydroxide ions or oxides. But the bottom line is they love to oxidize. So they're even more reactive. They're even better at pushing their electrons because they oxidize better. So it's something you should be aware of, that sodium's a more reactive element, and there's only one element here. These, if you notice, are stable forms right here. This is after potassium has done what? Lost its electron. Now it's stable. Chlorine, which is 1 electron away from being stable, has 7 valence electrons, gains 1, as nonmetals do, to become stable. And again, potassium is also an alkali metal, but after it loses an electron and becomes positive, it's as stable as a noble gas. So these guys are very stable. Okay, these protons here are if you think about a proton, H plus, it can only really gain an electron, so it's not going to be a reducer. It's an oxidizer. Okay, it loves to grab electrons from things like metals. So this H plus in a scenario with the sodium would either accept the electron or pull the electron. In the case of H pluses in metals, the reason why acids are corrosive is because they'll pull electrons from the metals. Okay, any case, so the H plus is not a good choice because it would be an oxidizer. So A is the best choice. Okay, number 5. In the diagram above, which the label arrows identifies hydrogen bonding in water? Okay, well, hydrogen bonding, let's understand what that's all about. Water is a classic case where we have oxygen, okay, and this oxygen being very electronegative and small, these 2 lone pairs out here, and then we have it bonding with the water molecule. Because of the nature of oxygen being very electronegative and also very small, it's able to pull this pair of electrons between the hydrogen and oxygen in the covalent bond very, very close to the oxygen. Makes it very polar. But more importantly, because hydrogen has 1 electron and 1 proton, it almost loses its valence electrons. So if I was to put this as, let's say, a red dot, okay, it's as if it kind of almost lost it ionically, almost a transfer. So what you have is just a proton dangling out here. We call this an electron deficient hydrogen because of the polarity and the smallness, okay, of the oxygen, that really, basically you're dangling protons out here. And so if I was to draw it as little protons at the end of the water molecule, you could probably see why the strength of the attractions are very big. Now, the idea that the oxygen is small enough not to envelop, that allows this proton to have a lot of surface area to attract other things, is what the H bonding is all about. Now, basically we said, maybe we've learned, in order to have hydrogen bonding, you have to have an electron deficient H, and you need to have F, O, or N. These guys are the most electronegative atoms, and they're the smallest in the second period and the second principal energy level. And because they have an n equals 2, and then size index is this quantum number, as you may have learned, these are small enough to allow the hydrogen to have a lot of surface area to attract, and these guys are electronegative enough to create that scenario of these electrons being pulled away. Any case, you have to have an H connected to these three to have H bonding and have electron deficient H's. So back to the problem. So where does hydrogen bonding exist in water? Well, first and foremost, this is an H that is electron deficient, so is this one, but they're both positives, and two positives will not attract each other. Okay, and so that won't work. And same thing here, these are two negative ends of the water molecule, they won't attract. This is a covalent bond between the H and the O. That's not what we're talking about. We're talking about an intermolecular force between molecules. So we're talking about, if you look at a molecule, what's the attractive force? And these are two molecules, and we're talking about D is the answer, where we had the electron deficient H of this hydrogen attracting the negative end of the oxygen's molecule. So that's why D is the answer. D, duh. Number 6. Okay, number 6 is very wordy. It's a kinetics experiment, so we're dealing with the rate of reaction. And immediately in my head, I go R equals K times whatever the reactants are. And then I notice I'm using my chalk, which I know is a weak base, and I'm adding an acid. This is acetic acid or vinegar. And the rate of reaction, the calcium carbonate, this is our Tums reaction. And the vinegar is determined by measuring a volume of gas. We should recognize the gas given off here is the CO2. Okay, and we've seen this reaction many times over. And of course, we're at 25 degrees Celsius in 1 atmosphere. Which of the following experimental conditions is most likely to increase the rate of the gas production? So, although I might have written this, now this is essentially what factors affect the speed or the rate of reaction. So we know there's a bunch of factors. Let's go through them. A, decreasing the volume of ethanoic acid solution used in experiments. So if I was going to use 100 milliliters of the ethanoic acid, okay, or my vinegar, if I use less, then I have less ethanoic acid to react, so I have less reactants. So if you think about it, having less reactants means you're going to have less collisions among the reactants. So if I take away some of the dancers on a dance floor, there's going to be less collisions. So that's not going to increase the rate of reaction. B, decreasing the concentration of ethanoic acid. So let's say I'm still using 100 milliliters instead of going down to 50 like, let's say, choice A is saying. Let's say I still use 100 milliliters, but instead of using a 1 molar solution, now I'm using a 0.5 molar solution. Well, that's doing the same thing. By lowering the concentration, you're going to have less dancers. And in this case, you're lowering the actual number of moles of stuff dissolved in water for the same volume. In this case, you're just lowering the total volume. Both of these, A and B, would decrease the rate of reaction by lowering the number of reactants and thus lowering the rate of reaction because you are decreasing the number of possible collisions. Okay. Decreasing the temperature, well, that's the speed of which these molecules will collide, and if you make them go slower, they collide less often, and thus less reactions would occur, so that doesn't make any sense. D, decreasing the particle size. Now we're on to something. If this is a solid, if you remember in our Tums labs, for those that were with me, we crushed it into small little pieces to increase the surface area so that the acid had an easier time to react with it. All right, so decreasing the particle size is increasing surface area. And when you increase the surface area, what you're doing is allowing more particles, more molecules, okay, at least in this case, more ions. You're increasing their ability to be collided with the acid. So D is the answers. Increasing the surface area always speeds up the rate of reaction. That's why carbon dust, whether it's um, dust from sanded wood toilet seat covers, or that's an inside joke, has to be, or coal dust or sugar dust, all of those things are explosive, okay, in the dust form because you're increasing the number of collisions that could happen, exposing them to more collisions. Okay, number 7. So number 7, they're giving me a reaction and they're saying that the value of the equilibrium constant is 50. Don't get lost if they say Kc. Kc just represents the idea that we have an equilibrium constant using concentrations. Kp would be with gases here. We have gases, but they're not using atmospheres. So tell me the Kc is 50, and they're telling me in this enclosed system that I have 2 moles of each at a certain time period in a 1-liter container. Okay, so this information is telling me that the concentrations of all of these guys, 2 moles over 1 liter, is 2 molar. So they're telling me I have 2 molar concentration of all of these. And again, why do I know that? Well, because molarity is equal to moles over liter. Okay, and since all these gases are occupying 1 liter, 2 over 1 is 2, and you can do that in your calculator, and you'll see that that is true. So what they're really saying to me is I've got a condition, and I know the K is this, but this is my current condition. What's going to happen? Well, they're giving you a Q, my friends, in chemistry. They're giving you a reaction quotient. Let's go figure that out. And we find our reaction quotient. We can see how far it is away from K to see if this reaction is going to move left or right. So we know that Q, just like K or KQ, KA, KB, it's products over reactants. Coefficients become exponents. Solids and liquids do not apply because they do not have a molarity. So what's my product? My product is HI. And we put a bracket to show concentration. And I put that squared because there's a coefficient. And then I have an H2. Okay. And then I have an I2. And I don't put any the coefficient will be a 1 there, but you don't have to write it. So there's my Q, and I know that I have 2 molar of everything. So let's just plug it in. Okay, so I got 2 squared. All right, and of course I've got 2 times 2. All right, and we solve for our Q. It's pretty simple math. You don't have a calculator here. We get 4 over 4, so my Q is equal to 1. All right, now what did they say in the problem? Kc is equal to 50. Okay, so my equilibrium is equal to 50. And as I love to do is draw this diagram. All right, and what's my diagram? Well, if I've got an equilibrium, which is the most stable position a reaction wants to always move to, here's my K, and I can see that my Q is less than K, so my Q is going to be over here, is less than K. And for those that didn't have me, this position right would be 100% reactants, and this would be 100% products. So because my Q is greater than K, because there's a lot more of these reactants than there should be, okay? Because K is a bigger value, which means my top number should be bigger. So we always know that we're moving always toward K. So because my Q is less than K in this example, the reaction is going to move it's going to be more spontaneous in the forward direction. My delta G is negative in the forward and positive in the reverse. So that means this reaction is going to become more spontaneous in the forward. And if that's the case, we have a shift to the right. And because of that, we say that more HI will form. If we're going to go more spontaneous to the right, we're going to build up our products and we're going to use up our reactants. And if you think this is like Le Chatelier's principle, you are right. It is Le Chatelier's principle. And it's explained through Q's and K's. So that's why B is the answer. All right. All right, so in number 8, they give us these Boltzmann distribution graphs, very, very important little graphs talking about the variation of molecular speeds that molecules have. okay? So when you have molecules at a certain temperature, you should be aware they're not moving all at the same speed. Some are moving faster and slower than others, so there's a broad range. And you may have learned that the most probable speed is kind of like this average. We call it the root mean square speed. And you may not have learned that, but the bottom line is there's a distribution around that average, some above and some below. If you learn about statistics and averages and standard deviations that talk about a bell curve and the variations from those positions, then that's something that makes a lot of sense. But all you got to understand here is that they're showing the speed distribution of molecules in the y, and we have a certain temperature. This temperature is staying constant, and then which of the graph shows the speed distribution at a lower temperature is a dash curve. Okay, so they're changing the temperature. It's not staying constant. But what we should know is that the dash curve, make sure we get this correct, is the slower. Okay, now if I look at choice A, it looks to me like there's faster speeds at a slower temperature, and we should know that that doesn't make any sense at a higher temperature. We know molecules have a higher average kinetic energy, and because of a higher kinetic energy, they have higher speeds. Now, kinetic energy is 1/2. Okay, that should be 1/2 the mass and the velocity squared. That's the speed I'm really talking about there. So higher the kinetic energy, higher the speed or velocity, and speed, of course, is just no direction. Okay, now we look at choice 2. We're looking at a colder temperature and the number of molecules just dropping, and that doesn't make any sense. The molecules is going to be the same, which means the area under these curves will be the same for each. The amount of molecules will stay constant. Here, this doesn't make sense because the number of molecules are decreasing. The area is not the same. Okay, and of course, if you look at C, a colder temperature, we also have a scenario where we're actually stretching this curve outward and having faster speeds at a colder temperature. That's wrong for 2 reasons, because, well, number one, this area is actually bigger than this one, so we're gaining molecules, which makes no sense, and we're having molecules have a higher speed at a higher speed at colder temperatures. Again, that doesn't make any sense. And if you look at choice D, that's the one that makes a lot of sense. Okay, if we're at a current temperature and a current range of speeds for, let's say, gas molecules, when you get colder, they bunch up. This area has to spike up if the variation decreases, and it spikes up because there's a limit here of molecular motion, and that, of course, is 0 Kelvin. There's no limit of how fast molecules can get theoretically, but there's a limit when they get colder. So when you get colder, they push back against this a little bit, and they have to spike up to maintain the what? Same volume. So this is what happens when you increase the temperature, okay, of molecules. They actually spread out. There's more what? There's more molecules at a higher temperature that have greater speeds. You still have this range, so it spreads out. If you notice what I drew here, it was trying to show that the area stays constant. So as temperatures increase, this kind of flattens out here, and as it gets colder, it pushes back against this limit here of 0 Kelvin, the coldest possible temperature. That's why D is the answer. Okay, number 9 is some basics of heat flow. Okay, they have a 100-gram sample of lead heated to 100 and quickly transferred to an insulated container like a coffee cup, holding 100 grams of water at 22, so very basic calorimetry type of scenario. The temperature of the water rose to a final temperature of 35. Okay, which of the following can be concluded? Now, if you're not seeing this, I always suggest draw what you have here. You have a container that's insulated, you have some water, and you added a hot block. Okay, and assuming it's more dense than water, it's at 100 degrees Celsius. And of course, the water is at 22. So you know from the second law of thermodynamics that heat's going to flow, okay, in a certain direction, certain pathway. It's going to go from hot to cold. So obviously heat's going to flow this way. The block is going to decrease in temperature. The water is going to increase. The same amount of energy, by them saying an insulated, and no, nothing is perfectly insulated, but we can assume here that the energy that was what? released by the hot block is gained by the water. Q of the water, okay, which is your equals the negative Q of the block if you want to go that route, okay? But so these values are just opposite and equal, have to be in a closed system. I guess we're assuming all that, but let's look at the choices to see what makes sense and what clearly doesn't make any sense. The metal temperature changed more than the water temperature did, and that's a true statement. You may forget that the Q, of course, is equal to what? Q is equal to the mass of the substance, some kind of specific heat, molar heat capacity maybe, okay, times the temperature change, temperature final minus temperature initial. And what you should know is that metals are better conductors of heat than water. So they're going to have a much lower specific heat or energy cost to change their temperature. So the metal is going to actually have a greater temperature change. Okay, it easier gets warmer. That's why you put your hand on a, we can say, handle of a pot that doesn't have any wood or anything on it. It's going to hurt your hand. Metals conduct heat very easily because it doesn't take much energy for them to change their temperature. Okay, water takes a while. Okay, that's why, you know, our oceans take forever to warm up and cool. They have a higher specific heat. So if we deal with water, its higher specific heat makes it harder for its temperature change. Okay, so that statement here makes sense. Metal temperature changed more than the water temperature. Yes. Now this part, I'm not sure. Therefore, the metal lost more thermal energy. That's wrong. Okay, the Q's will be the same. It's the C's that are different. Okay, and because the C's being different, okay, our temperature changes for them. So this is going to be the same joules of energy released and absorbed because the C goes down, okay, this temperature has to go up for the same value of Q. Same thing over here, they equal each other. So if the C is going up for water, higher specific heat, higher cost, takes forever, the temperature change is going to be smaller. Okay, so that doesn't make any sense. Okay, B, the metal temperature changed more than the water temperature did. That is a good statement there. Okay, there is going to be a greater temperature change because the specific or molar heat capacity of the metal, okay, is going to be lower, so a greater temperature change, which speaks to the fact that metals are better conductors of heat. Okay, whereas the water, as we just spoke about, will have a smaller temperature change. Okay, but the metal lost the same amount of thermal energy as the water gained. Correct. The same amount of energy that is absorbed is lost. Remember, temperature change isn't a direct measurement of energy. Okay, you've got to consider how well you change your temperature. That's what really this molar heat capacity is, and how much of the substance you have. All right, so the heat exchange was exactly, the temperature change will not be because of the what? The ability of the different substances to conduct heat, molar heat capacity. Okay, the other two choices are not, do not make any sense. They're just trying to distract you. Okay, so let's continue. Okay, so number 10, we're dealing with one of the newer types of multiple choice questions that we're running into, and that is dealing with mass spectrometers. Okay, so this is essentially the data that we collect from a mass spectrometer. And if you remember, a mass spectrometer is going to have a scenario like this. That keeps happening. Okay, but what it does is essentially it's like almost like a cathode ray tube in a sense. But what we're going to have is we're going to have a scenario where we're going to take some sample, whatever that sample may be, and we're going to pull an electron away from it. Okay, so it's kind of like the opposite of a cathode ray. We're going to basically have some charge here, and this is going to have a negative charge on this side, and essentially our atom, okay, we're going to put a positive charge on this side, and we're going to try to pull an electron away. So you'd have kind of like a cathode ray coming back, and the rest of the sample, the ion, sometimes called a canal ray, but the rest of the ion, the positive ion, would be pushed through this way. And then we have a magnetic field, okay, that surrounding this tube, which is going to try to basically draw it, bend it, and push it in a certain direction. And essentially, we're going to measure the distance by which it hits. So this movement of the positive charge creates a magnetic field, and basically we're making it from hitting the side. So we're basically creating a magnetic field here so that it doesn't hit the tube. And we basically adjust this so that it doesn't hit the sides here. We'll adjust it. We want to bend this and give it some kind of push on it so that the lighter molecules would hit closer to the detector. The heavier molecules would be less affected by the field and be able to move farther. So just based on mass alone, okay, momentum, okay, having more mass, you'll be able to be less affected by the magnetic field that's kind of pushing down on it. All right. And the heavier ones would be less affected by that field than the lighter ones. And the distance by which you can compare where they hit gives you a relative, and I say relative because it's based upon, one position to another. That's why you hear the word relative. You get a relative mass or difference. The heavier ones would be able to go farther than the lighter ones, and you could measure that distance, and you could calibrate it for how many units are in between, and based on how many hits you get in certain positions, okay, let's go back there. Based on how many hits you get in a certain position depends upon how much relative abundance you have. So if there's a lot of hits in this position, we're going to get a lot more what? You're going to get a lot more, you can measure the percentage of those particles that hit there. Now, the sample we have could be a pure atom, and as we've learned, atoms have different, what we call isotopes, and iso means same, and this is very important. Isotopes are the same form of the atom, but they're just different what? Different masses because of different number of neutrons. Case in point, we have carbon-12 and carbon-14, two very common isotopes of carbon. Not all of them, by the way. Carbon has atomic number 6, therefore we know that this carbon has 6 neutrons, 12 minus 6 if you remember that, 14 minus 6, this one has 8 neutrons. So if we put carbon in a mass spec, we will get clearly two different positions if these are the only two isotopes available. Obviously there is a couple more, but very low percentages wise. You'll get two major hits, and the one that's in most abundance will have the bigger size, would be, as you guessed, carbon-12. Okay, so that's what this is about. You're going to see this. So in any case, we're looking at the relative distances they're hitting in this mass spec, and we're seeing how often they were hit at those positions. And this can give us something about how many of different types of isotopes exist in nature for that sample. So back to the question, the elements I and T have similar average atomic masses, and that's true. If you go to your reference table, you will see iodine and tellurium both very similar. Okay, tellurium Te has an atomic mass of 127.60, and iodine is equal to 126.91. So they're very similar. So the question reads, all of the following statements, so in any case, the elements I and T have similar average atomic mass is true. A sample that was believed to be a mixture of iodine and tellurium was run through a mass spec. The resulting data above appeared. All of the following statements are true, okay? Which would be the best basis for the concluding that the sample was pure tellurium. All right. Well, again, we're really thinking about isotopes and all these different isotopes. Let's look at the questions. Tellurium forms ions with a -2 charge, whereas iodine is a -1 charge. Well, that's true, as they said, but in a mass spec, we tend to pull off just one electron to make it a +1. So that really doesn't come into play that they make different ions. We're really talking about their different masses, okay, due to their different number of neutrons in their different forms called isotopes. Te is more abundant than iodine in the universe. Well, again, that is a tough one because I don't know where I got my sample from. Was a sample from an ore of tellurium, or was it a sample that was just out in the air, so you really can't make any determination about the abundance in the universe. You can talk about the abundance of certain isotopes. If this was all tellurium, I could say, okay, tellurium 130, Te130, this specific isotope is the most abundant, okay, possibly, but I can't talk about just tellurium over iodine. That's a silly statement. I consist of only one naturally occurring isotope with 74 neutrons, whereas tellurium has more than one isotope. Now they said all of the what? Statements are true. So if this is a true statement that we know that iodine consists of only one naturally occurring isotope with 74 neutrons, okay, think with me for a second. If I've got 74 neutrons, and I can write 74 here, neutrons, and I know that iodine, okay, from my reference table, I'm just reading this as 126.9. We can round that to 127. Atomic number is 53. And then when we subtract, okay, we're going to get 74 neutrons. So that makes sense to me. So that would mean that I would need to have iodine 127 or a 127 number. And we look here, 127 is missing. So therefore, there is no iodine in this sample, if in fact there is only one naturally occurring isotope. But they said that all the statements are true, so that clearly is telling me that this mass spec data from a sample could only be all tellurium, because there is no 127 there. So clearly that's the best choice. Besides, it's the only one that's talking about isotopes. All right, higher first ionization energy, that's not going to matter. Once we pull the electrons off, okay, we're going to measure the distances they travel based on mass. So 10 is C. And again, I spent time on here because you're going to see more mass spectrometer questions, okay, and that's the basis. So number 10. And now number 11. So number 11, we have some reactions represented above. An aqueous solution of oxalic acid. Which of the following represent a Bronston-Lowry conjugate acid-base pair? Conjugate is the same chemical, plus or minus a hydrogen. So we're looking for a conjugate acid-base pair. We're looking for something that is the same chemical plus or minus an H. Okay, if you look at choice A, we have H2C2O4, C2O4 negative 2. This differs by 2 H's. No, it has to always differ just by one proton, not two. You say, Mr. Grotsky, why does it matter? Well, as you remember, each proton that comes off the acid has a different Ka. So it definitely matters which one you're talking about. There's a different amount of the ability of the proton to leave the acid in a diprotic scenario as this is. So you got to consider just one movement at a time, and that's why B is the answer. We have C2O4 negative, and then we have C2O4 negative 2. This differs just by one H. Look at choice C. This is not the same chemical. This is not the same chemical. These are not conjugate acid-base pairs. Okay, now this could be, but if you notice, this has 3 H's and this has 1. So these are differing by 2. So you can't differ by 2 H's. Even though these are the same chemicals, they're plus or minus 2 H's. So we have to only differ by 1 H, and that's why B is the answer. C is the worst answer because the conjugate acid-base pair are totally different. These are not the same chemicals. So 11 is B. Okay, number 12. And this is a classic. Okay, here we go again. Number 12, here is a classic AP multiple choice question where they want you to evaluate the signs of the Gibbs free energy equation. So in this question, they want to know, very important, which of the following reaction is not thermodynamically favored? That would mean a delta G that becomes positive, becomes positive at low temperatures, but becomes favored and temperature increases. So when temperature increases, delta G can move to the negative value. But we want to know when the low temperature. So what we're going to start with is our formula. Delta G, and this is right off your reference table, is delta H minus T delta S. Okay, now low temperature. This is what we're going to affect. We want to make this low temperature. Now think with me just the way the formula is. If I was to lower this temperature, okay, that means I'm going to make this entire expression, the way that I have it written, more negative, okay? More negative if the way it's written. So if it's more negative, that'd be a good thing with lower temperature, okay? So we're trying to not be thermodynamically favored here. So let's think about some values. So let's put in our delta S to see what's going on here. If I was to put in a negative delta S, like choice A, which is not a good thing, it's a unfavorable scenario if your local system has a negative delta S. But let's put that value in here. If this is negative, and then we have this negative, then T is standing here, you can see that this becomes a positive value, okay? And if I lower, and the reason why I just went positive there, for those that didn't see, a negative times a negative gives me plus plus, okay? It's important you realize that. So the way that I have it written here, okay, if I put a negative value of delta S, this becomes a plus plus. Okay, now you can say, okay, great, that positive value is going to make my what? Delta G positive. But if you do what? Lower the arrow of temperature, it's going to make this positive part of my equation become what? Less positive and thus more negative. So you can see having a negative value of delta S creates a scenario we do not want. A lower temperature with this scenario would make this less positive, and inevitably delta G becomes a chance to become more negative in the process. So that's a scenario that doesn't work for us. So we're going to have to work with delta G becoming positive. Okay, so watch what I do here. It's minus T. Now delta S is going to be positive here. Okay, and you say, again, I'm still not following you. Okay, well, just stay with me for a second. Let's see how this plays out. Now, just like before, just with my negative numbers, I'm going to make this plus, and this becomes a negative. Let's think about this. Plus a negative. Okay, and now you understand this scenario. By making this plus a negative, we notice the value of a positive delta S, which is favorable in the system's entropy anyway. Okay, this now becomes plus a negative, which means just based on what I have here, delta G is negative. But if I was to lower my T in this scenario, I'm going to make this less negative, which means less negative at low enough temperature. If this is less negative enough, this will drive it to become a positive delta G, right? Plus a negative, make this less negative by the T times it dropping enough. That's what they're talking about. It'll make the delta G become a positive at some point if the temperature is low enough. So that clearly tells me that my delta S has to be positive. Now, what about this value? Okay, well, if you think about it, if I'm trying to make this less by lowering the T and making this negative value now because of the plus negative scenario, by making this a lower negative, this becomes positive, but that's only going to work if delta H is already positive, which is endothermic. So let's talk about it. Delta H, it's positive, like this scenario, minus T delta S, that's also positive. Look at the values again. See if this works. You really got to bear down here. You can do this, okay? And they love to give you these questions. So I do my plus a negative value, knowing full well that that's really a positive entropy, but this expression is all negative now. So if I lower my T, I'm going to lower the negativity of this entire expression, and this could get positive only if this is already positive. So that's the reason why a positive delta H and a positive delta S gives me that scenario. Now, what do they say in the second part? If I increase the temperature, delta G will become negative. Well, if I reverse this arrow and make it go up, now the negative part of the expression can overtake this positive, and we would call this an entropy-driven reaction, where we can now make it negative. The only scenario that we can decrease the temperature and make it less spontaneous, less negative, would be the positive delta H and positive delta S. And also, the only scenario where we can increase the temperature, okay, and make it go from that scenario to even more negative has to be delta H being positive. So that's why the second B is the best answer. And again, go through this, see the signs, okay, because this is a question you will see. 12 is B. Okay, so number 13, another one of those visual representation questions, okay, illustrations they love to now have in this test, okay. So which particulate or particulate diagrams best shows the formation of water vapor from hydrogen gas and oxygen gas? So you should realize that this is the reaction you're dealing with. Hydrogen gas is diatomic, okay, and I'm definitely getting old of that happening, right? So hydrogen gas is diatomic, so it's H2. And we would say oxygen gas, also diatomic, in its elemental form is O2, something you really have to know. And we're going to make water. Okay, water vapor or just water. And if you balance the reaction, you're going to see that you need 2 of these and 2 of these. Now, what does this mean on the molecular scale? It means that very simply, I'm going to need 2 hydrogen molecules. And I'm going to need, okay, 1 oxygen molecule. That's the 2-to-1 ratio, if you want to put the 1 there. And what's it going to make? It's going to make 2 waters. Okay, and I put them in there, and I get 2 H's apiece, little Mickey Mouse ears, and you can see that's the scenario. Okay, so what they're saying to you, all right, you got a rigid gas which the following best shows the formation of water. So in my opinion, we better show the appropriate ratios. So first of all, A doesn't make any sense because it's basically saying to you, you don't know that these gases are diatomic, so we get rid of that. And B for the same answer, okay? These gases are clearly diatomic, and for those that don't know, I like to use the word Hofbrinkel. Some people use Brinkelhoff or any kind of other mnemonic works. These all like to become, okay, diatomic. So the Hofbrinkels or Brinkelhoff, okay? And so now we got C and D as we start seeing the diatomics appear, and that should wake you up and say, oh, okay. So which one is showing the correct ratio? So we should have twice as many what? H2s as water. So you got 1, 2, 3, 4, 5, and 6. That's good. And then 1, 2, 3. And then we have 1, 2, 3, 4, 1, 2, 3, 4, 5, 6 waters. Okay, so which that looks like a good ratio. Okay, here I have 1, 2, 3, 4, 5, 6, and then for my oxygen, 1, 2, 3, 4, 5, 6. Now this would still react, but as you can see, you would need some what? Excess. There's a limiting reagent. Here we have the correct ratio. There's twice as much hydrogen as there is oxygen, okay, which is the darker color ones. And we have the right number. Notice the number of water molecules is the same as the hydrogen molecules. We got 6 and 6. Here we got 6, and that's correct. That would definitely happen. But as you know, we would also have 3 unreacted hydrogens. Okay, I'm going to say 3 reacted oxygens here, right? Because we have 1, 2, 3, 4, 5, 6. So that's 12 H's over here. And we have 12 H's or H atoms over here because we have 6 water molecules, 2 H's apiece on the ears of the Mickey Mouse. But we also have 1, 2, 3, 4, 5, 6 times 2, 12 oxygens. And here we only have 6 oxygens. So this can't work because of the law of conservation of mass. So what you would have is you would have 3 unreacted oxygens. And that could be in a drawing. And that would be correct, but they're missing that, so this choice is incorrect. C is the best choice. That follows the law of conservation of mass based upon your balanced chemical equation, which is an application of the law of conservation of mass and stoichiometry. Okay, moving on. All right, cool. I've got my acid and base question here with a titration curve. Loving it. So in number 14, we have a, I'll get this down. Number 14, okay, we've got ourselves a titration curve, and one thing that jumps out to me is the equivalence point. Boom, is about right there, and it's greater than 7. So if the pH of my equivalence is greater than 7, then I know that clearly I must be titrating a weak acid with a strong base. Now, how do I know that? Because a weak acid is going to produce a conjugate base that can ionize water and then react with water at this point to drive up and produce hydroxides. Okay, or if you just think the strong base is going to pull the weak acid to equivalence above a 7, if you think of it that way. But I know I have a weak acid scenario, so that tells me that this is a buffer region. And S, if this is my 40, is my what? Equivalence volume, then 20 is going to be the volume at the max buffering position where the conjugate acid, okay, whatever that may be, HA, okay, is equal to the conjugate base because the base drove it into the halfway position. So at point R, okay, so at point R, I'm a little bit below max buffer, which should tell me that there's a little more what? HA is bigger than the A negative. That's why the pH is lower. Remember this Henderson-Hasselbalch equation, pH is equal to the pKa of your acid plus the what? Log of your conjugate base, I should do A minus actually, over the acid, which is given to you in your reference formula. So if I've got what? R, I've got less, okay, I've got less of my conjugate base. So this top number is smaller and this bottom number is higher. So this gives me a lower log, less than 1, which makes it a negative value, and it lowers my pH because it's less than my pKa, right? A lower top number and a higher denominator, that's going to be a number less than 1, and a log of something less than 1 becomes negative, and you're going to add a negative to your pKa, you're going to be a little bit below. So I know that my conjugate acid, which by the way is weak, who hates to dissociate, that's what it means. A weak acid barely does what? It barely goes forward. We have strong acids that completely dissociate, and we have weak acids that barely dissociate, okay? There is no real in-between, as we've learned. So it barely goes forward, so it makes sense that we're going to have a lot of HA. Look at our choices. The question says, which has the highest concentration? Well, we know the HA beats the A negative because of where it fits on the buffer region. It doesn't beat out water, so that's not there. It wouldn't be H3O plus because, well, the amount of H3O plus, if the pH is at this position, let's say it's 3, the H plus concentration is 1 times 10 to the negative 3. That's tiny. And the hydroxide's even smaller, 1 times 10 to the negative what? Negative 11. So these concentrations are extremely small compared to how much HA we've added or what we would have. And now if you know the base is 0.1 and we used what? 50 milliliters of the acid is sitting in the beaker at 40 milliliters, we basically did what? We neutralized it. So the acid's concentration is very similar to the base's, which is so much bigger than these values. Clearly A is the best choice. Okay, great question. Another particulate diagram making you really understand what's going on. So what's the best particulate representation drawing except other than water that's present in significant concentrations at point U? Now we should know that point U is at some pH and volume that's beyond the equivalence point. And as I've taught you, anything beyond this point is just the extra titrant. In this case, we've just added extra hydroxide in water. Beyond this point, okay, there is no more what? Acid truly left, okay? We've driven it off into conjugate base. So what's happening? Well, if you look at A, very quickly, we have equal amounts of conjugate base and equal amounts of Na. Now, Na is the spectator that came from the base. We added NaOH. So we drove the what? We drove the acid all the way to completion by adding the strong base. And if we have equal amounts of Na plus and conjugate base, what does that mean? Well, this must be the equivalence point. A is representing this point. We added just enough of the base, of course, that was NaOH, and that reacted by yanking a what? An H away from the HA to make water, and you're left with that. Because these are in equal conditions, this could have been a choice for the equivalence point. Okay, and that's why that's not correct. If we go down to C, and I'm showing you why the other incorrect choices don't work, because you could see this question asking something different. So in letter C, look what we have here. We have equal amounts of undissociated acid with dissociated conjugate base. Hey, notice there's equal amount of what? Base, or at least the ion that came from the base. So NaOH dissociated and pulled what? The OH pulled the H from the water, and because we have equal amounts of sodium ions left over with conjugate base, this means that this represents the half what? Titration point, because we have equal amounts of HA, undissociated acid, and equal amounts of undissociated base. This is max buffering position. Why? Again, we have titrated it. So this would be, if I was asking, this would be for position S. D, we have what? More conjugate acid than conjugate base. Notice the Na plus and conjugate base are the same amount. As I add base, these will be equal. This is point R that we just talked about in the first question. So at point B, or at least question B is the answer, we have a heck of a lot more what? Sodiums, okay? Then we do have conjugate bases because we added extra what? Hydroxides. And notice we actually have extra hydroxides hanging around. There's no what? Acid left for it to react with. So that's why B is the correct choice. Okay, so number 16, they're saying at which point in the titration is the conjugate base closest to twice of that of H of A. So we know the equivalence point is right here. We know the max buffering when they're equal is right here. So if there's more conjugate base, T is the best choice, where that we would have something closest to twice of that. Now again, if you don't see that, Henderson-Hasselbalch, pH equals the pKa plus the log of the what? Conjugate base over the conjugate acid. If you're going to have a bigger conjugate base and a smaller HA, this expression becomes a positive, and the log stays positive when it's greater than 1. And we would add to the pKa, and you know at this position here, the halfway titration point, remember the equivalence point was at 40 milliliters, the halfway point that would make equal in numbers so that the pH equals the pKa here is at 20. So this is the pK value. And we're going to be above that because having more A, conjugate base, means we drove it forward even more by adding more base. We dropped base into acid. So this number is going to be greater than 1. This stays positive, and we add it to this Ka. It's going to be below the equivalence point, but somewhere in between. T is the best place where we have a scenario where we have more conjugate base than acid, but still under the equivalence point. Okay, so number 17, student carries out a titration but uses an indicator instead of a pH meter. If the indicator goes slightly past the equivalence point, okay, now we would love to know exactly where this occurs, but if we did it slightly past the equivalence point, maybe we get a volume at the equivalence that's bigger than it's supposed to be. Okay, so the question is, what will the students obtain for the calculated concentration? All right, well, what do we know? We do know that at the equivalence point, where this line here, as we should be able to identify from our curve, was 40 milliliters. Now that 40 milliliters becomes 0.04 liters, and I put that right into liters. For those that had me in my class, you know right away we're going to put that in liters. Okay. In any case, what do we know? Well, we're going to find out how many moles of base were added. So 0.04 times, I know we don't have a calculator, and we have how much in my beaker. In the beaker in the question, so we find this 0.04 liters as the amount of base we had to add to the equivalents. We're going to times that by the concentration of the base that we know, and the concentration of base given to us in the beginning of the question was 0.100. So I'm going to times it by 0.1. Now, why am I doing this? Okay, this is the molarity. Okay, what would we know? Molarity is equal to moles over liter. So by solving for moles, we're just timesing liters times molarity. And liter times molarity, which is mole over liter, okay, gives me, of course, moles. So we should know right away that 0.1 times 0.04 is 0.004 moles. So at the equivalence point, this is the mole of base that was added. But at the equivalence point, that equals the moles of the what? Acid that were added. So the moles of the acid are equal to that. All right. So if we continue on, we're going to use the moles of the acid, which is 0.004, and we're going to divide that not by the total volume at that point, but at the volume that's in the beaker. And as we go back to the problem, you can see that we had a 50 milliliter sample, so we have 0.05, okay, liters. Okay, so what's the molarity there? So I'm going to have to use some shorthand if I don't see the answer. So 0.05, and again, what I'm doing here is finding the molarity, the moles over the liters of the acid. I know the moles of the acid because they have to equal the moles of the base at the equivalence point. So now I'm going to have to do some math longhand, 0.05, and I'm going to use 0.004. And using our basic skills here, 1, 2, 1, 2. Okay, and what do I get? Well, 8, I'm going to have to go with 0 here. And I go 0.08. 8 times 5 is 40 here. So you can see that you get 0.08 molar for the acid. That's at 40 milliliters, as I just talked about. But if the indicator is a little past the equivalence, we would be adding something greater than 40, like 41 or 42. And what would that do? Well, having more, that would increase my moles of what? My base added, and it would increase my moles of the what? Acid that we think we have, which would increase my molarity above 0.08. Okay, so that's why slightly more than 0.08 is the answer. Okay, so number 18 and 20, we have this nice little chart here. We've got 3 gases, and we have some alkane single bonded hydrocarbons. You don't have to know that, but I'm just kind of looking at this, and I see that they are increasing in their molecular size, and I can see the temperature is constant, and I'm looking carefully and I see that, ooh, there's a pressure difference there. So there's an anomaly here. And as I look at 18, the average kinetic energy of the gas molecules is what? Well, the average kinetic energy is basically average of all the thermal energy of all the molecules, and we know that average kinetic energy is essentially proportional to temperature, and since they're all at the same temperature, they all have the same average kinetic energy. So that's all D was about, was finding and understanding that kinetic energy, average kinetic energy of the molecules will be the same. Now people confuse this sometimes because they want to believe that, wait a minute, I've seen these Boltzmann distribution graphs where I looked at number of molecules, let's say here, and I've seen that at, if I have the same, this could, let's say, make this, some gas, let's say make it chlorine gas, and then they've seen, well, I've seen scenarios where under the same temperatures I have my helium gas, and they clearly have different molecular speeds, and that's true. But remember that kinetic energy is equal to 1/2 the mass velocity or speed squared. So kinetic energy is not exactly the same thing as the velocity. In the case of helium, there can be different speeds, but the overall what? And I keep mentioning this because people will confuse kinetic energy with the speed. And although there's a proportionality to it, it's not the same thing. If you've got a bigger mass like chlorine, you're going to have a smaller velocity or speed for the same kinetic energy, right? It's an inverse relationship. That's why you talk about how fast molecules move in terms of the Graham's law of effusion and diffusion. Heavier, massive, okay, molecules, okay, have slower speeds. So that's something I just keep mentioning because people will confuse average kinetic energy with the actual molecular speed, okay? Any case, number 19, the density of the gas is greatest or where? They're asking for greatest. Well, density is mass over volume. And you notice we're at the same temperatures, and you notice there's different masses here. Okay, so you might expect, well, the heavier mass, butane, okay, molar mass, would be the more dense gas. Okay, but careful, as I said, the anomaly here is that there's a different pressure. So with having twice as much pressure, we're going to pack this gas in tighter than we are the other gases. So they have, again, the highest density should be this gas. Now, for those that were studying manipulations of the ideal gas law, okay, you should remember that we can derive, I always have my students remember dirt over P, okay, molecular mass is equal to dirt over P, and that's density. If you solve for density, okay, you get density is equal to PM over RT, and if you can see, higher the pressure, okay, yes, molecular mass is there, but 30 to 58, the bigger monkey in the room is doubling the pressure for the same temperature. The molecular mass is a little bit lower, but not as big as doubling the pressure would increase the density more for gas B. And if you want to do it intuitively, okay, I'm sorry, sorry, that's right, it is B there. So if you want to do it intuitively, yeah, the mass is bigger for C, but doubling the volume, you're really going to cut the, doubling the pressure, you're going to cut the volume in half. So you're really going to have the most densest gas with the greatest pressure. Okay, so 19 is B. I don't care if you think about these equations or think of intuitively, okay? Either way is a good way to go about your business. So number 20, if the pressure of each gas is increased at constant temperature, until condensation occurs, which gas will condense the lowest temperature? Now, what are they after here? They're after the idea that if you increase the pressure enough, you're going to force these gases closer together until they are forced to attract themselves into a liquid. So we're saying which gas will condense at the lowest pressure, meaning who is going to condense first, right? Because you're going to increase the pressure, so the ones that condense first will do so at the lowest pressure. So what they're really asking is who is going to condense first, and the ones who condense first, okay, are going to have the strongest intermolecular forces of attraction. So you start pushing molecules closer together, the ones that start becoming liquids that attract each other have the strongest intermolecular forces. So if you look at these compounds above, we should see that they're all hydrocarbons. And as we've talked about, hydrocarbons are always nonpolar. The carbon to hydrogen bond is essentially nonpolar in the sense the difference between electronegativities is very low. So it's not about the shape, okay, in terms of that. So these all have London dispersion forces, okay, and they all have clouds of electrons. So the question is, who is more polarizable? Who is going to make that cloud shift momentarily more to give a more negative? And the longer hydrocarbon with the biggest carbon chain, and that's butane, is more polarizable because being longer, those electrons have a greater opportunity to shift and deform their shape to create a more polar area. You also talk about the number of electrons are greater. The more electrons you have and the more polarizable shape you have, okay, the greater these momentary shifting of electrons in London dispersion forces. So gas C is the winner that would have the greatest attractive forces, and that's why it has the it's going to have the lowest, I'm sorry, the biggest, I say, boiling point. And in fact, once you start getting to 5-carbon hydrocarbons that are alkanes, they start becoming liquids. In fact, this, if I'm not mistaken, has a -1 boiling point. Okay, or I'm sorry, about 5 degrees, somewhere in there. So it's not as low as you think it is. And ethane and methane are way below -degree Celsius temperatures, where this one is at about positive or close to, because of that polarizability and great number of electrons that increases its LDF forces. Okay, any case, so that would mean that my butane, okay, would condense first because it has the greatest number of intermolecular attractions. Number 21. The mass percent of carbon in pure glucose is 40%. Now, anytime you're dealing with mass percentages, okay, I think immediately empirical lowest ratio formula. We cannot in the lab use percentages any other way. If I have a 50% by mass percentage, I don't know if the ratio is really 2 to 2 or 4 to 4. You don't know. It's just 1/2 of them, or 1/2 the mass. Now, of course, I'm doing molecules here, but so you don't know in a percentage what the actual real ratio is. You just only know the lowest ratio. It's important to realize when you deal with mass percentages. Okay, so mass percentage, okay, is 40%. A chemist analyzes an impure sample of glucose and determines that the mass percent is below that. Okay, so we're below that. We've got a -% error. Which of the following impurities could account for a mass percentage of carbon in the sample? Okay, well, let's look at some examples. Let's look at ribose. Now, ribose, okay, it's C5H10O5. Okay, if you notice something, it's a 1 to 2 to 1 ratio of carbon to hydrogen to oxygen. Well, what's glucose? Glucose is C6H12O6. So that's a 1 to 2 to 1 ratio. So if you had some ribose impurities, even though it has a different molecular formula, it has the same exact ratio percentage-wise, that would not lower it. It wouldn't change it whatsoever. Okay? And look at fructose, C6H12O6. It's an isomer of glucose. For the same reasoning, it's got the same ratio, so it would have no effect. Okay? Now, if you look at sucrose, let's put sucrose over here. If you look at sucrose being being C12H22O11, this might be a possibility here. Okay, now if we look at glucose being C6H12O6, you say, okay, this would be C6H11O, what, 5.5. Now, thinking about this, you may say, oh, it's under the 12 and the O, so you might be tempted to pick this one. Okay, but careful here. When I reduce this to the same number of carbons, there's less hydrogens and less oxygens. That would mean that this carbon has a greater percent of carbon in its molecule than glucose. And if that's the case, okay, that would contribute to a larger error, because again, if you just compare the percent by mass of carbon, there's a greater percent by mass of carbon in the sucrose. Therefore, and that's a hard one. Going fast, you may say, oh, it's under, but in truth, because these are lower for the same number, this carbon would have a greater percent by mass of carbon, and therefore contribute to a what? A larger okay, percent error. So that's not the answer. And so we pick for just by cutting out those that don't fit. A process of elimination, okay, water, okay, is your best bet here. If you notice, it's a 2-to-1 to water, just like the 2-to-1 here, but there's no carbon here, okay? So this is your best choice, A. And a couple more points about this. Don't forget that we're talking about the mass percent of carbon. So this would have a greater percent mass of carbon for the sucrose. And also in water, because you're going to increase the oxygen and the hydrogen components, okay, that means that the percent of carbon with extra hydrogen and oxygens from the water would decrease it, okay? So that would makes more sense, I think, continuing on with that fashion. All right, so it's the mass percent of the carbon. It has to decrease when you add the water because you're not adding any carbons. You're increasing the O factor, the oxygens and the hydrogens from the water, so the percentage of carbon has to go down as the mass gets bigger to these atoms. Okay, number 22. Number 22 is a nice little pH acid-base equilibrium problem. We've got ourselves a weak base. It's got a Kb, okay, very small. The pH of the solution of caffeine, the weak base, is this, okay? So they want the pH of a certain solution, so they want the pH. Okay, well, what's going on here? Well, we have C8H10N4O2, it's our caffeine, and it's a weak base, so what does it do in water? Okay, what do bases do? They're going to essentially grab H's, okay, and they're going to make hydroxides. And of course, I'll just write the conjugate acid. That's the compound that's there, but it'll be positive because we're gaining an H plus there. So there's a conjugate acid, and this is the conjugate base. So what do we know? We know the Kb value is 4 times 10 negative 2. We're going to need that in a second, but we want to know what the equivalent is. So I want to know the concentration of these things at equilibrium. We know there's a 0.01 initial solution, and there's our ice table here, 0.01, and this is going to be 0, okay, and 0, and this is going to be minus x, and these are plus x, and you can see what we're doing here. And this is going to be 0.01 minus x, and this will be x, and this will be x. And a lot of people at this point have seen this so many times, they know that it's going to be Kb is equal to x squared over 0.01. I'm getting rid of this x. I'm approximating it away because it's going to be such a small number compared to what? Compared to the value you have here. So you should realize that that's going to be Kb is x squared over 0.01 if you've done enough of these problems at this point. And again, I'm approximating this away. And the reason why this is x squared, what is Kb? Kb is equal to, okay, what Kb is equal to the products over reactants, coefficients become exponents, and solids and liquids do not apply. So the Kb, if you don't see what I'm doing, I know for some people you see this right away, but some people are not. It's going to be the hydroxide ion concentration times the what? The conjugate acid, which will be positive, all over the reactant, which is the caffeine. We'll just put CAF here. The water we wouldn't add because it's a liquid. We only put solids and liquid. We only put aqueous and gases. Solids and liquids do not apply because they do not have any molarities. So if you thought this would be the x, this would be the other x, and this would be 0.01 minus x we get rid of, and that's how I got to this value here. So let's put the values in, have some fun, and we got essentially 0.01 over x squared equals 4 times 10. Let's just get this out of the way now. Okay, and this will be 4 times 10 to negative 4 equals this. And people kind of fret a little bit sometimes of the math, but 0.01 times this, basically I'm timing it by 100th. This is going to get smaller by 100 times, right? If I was timing it by 1/10, this gets smaller by 10. So I'm really taking, this is really 10 to the what? Negative 2, and I'm timesing them. And when I times numbers, the exponents you add, so a negative 2 and a negative 4 gives me 10 to the negative 6, right? All right, the 4 in front is going to be maintained because this is 1 times 10 to the negative 2. And that's going to be equal to what? So 4 times 10 to the negative 6 is equal to x squared. And square root both sides. And you say, my gosh, how do I do this? Well, when you square root a number that's an exponent like this, you're basically cutting in half. Because what number times itself in exponent land? So 10 to the negative 3 plus 10 to the negative 3. So this becomes 10 to the negative 3. And the square root of what 4 is 2. So this becomes 2 times 10 to the negative 3. And what's that equal to? X now. Okay. And then, of course, my X is my hydroxide. And, of course, we're going to round this to 1 to make my life easier. We can do that. So 1 times 10 to the negative 1 is really 0.003, or 10 to the negative 3. And that's what equals my X here. And what I'm going to do is find my POH. So to get from this to the POH, all right, do negative log of it, which is nothing more than making this exponent positive. So I've got that my POH is equal to 3. And then to find my pH, it's 14 minus 3. That's how I always like to do business. So my pH is approximately in the 11 range, about 11, because we did what? Rounded off here. So that's why I got choice D. So this was an equilibrium problem. I went a lot slower here, but definitely you should be able to get to this little red box pretty fast. Okay, 0.01 times 4 times 10 to the negative 4 becomes 4 times 10 to the negative 6. Square root both sides. Square root of 4 is 2. Square root of 10 to the negative 6 is 10 to the negative 3. I got rid of this 1 here, just approximated away, only because we're just basically trying to find a rounded number. These choices are so far apart that I can do that. It's a good technique to round your numbers to make life easier. Don't expect you to be able to do that in your head. So by rounding and by having choices that are so far away, we can approximate our answers. So having 10 to the 3 made my world so much nicer. That became a POH, a negative log. And then I subtract my POH from 14 to get my pH, which is about approximately 11. The only choice with 11 there was D. So that's a really important one to review in terms of acid-base chemistry and dealing with some kind of math problem here. Okay. So number 23, Lewis dot diagrams of CO2 and SO2 are given to you above. How nice. The molecular geometry and polarity of the two substances are. Well, the geometry tells us something with the polarity, right? If we know the geometry, we can make good estimates about the polarity, about the places where there could be differences in charges if there's differences in the molecule or asymmetry. So I know that this is linear. There's no lone pairs above the C, so this stays linear. So the polarity in this type of molecule is right at the ends of the oxygen, but because they're on equal sides, there's no difference to one side, so nonpolar. This guy's got a lone pair, and although it's drawn this way, this lone pair repels these other pairs downward into a bent shape. And that bent shape makes these O's in an asymmetrical area. And even though there's some resonance here based on this is drawn that adds to some stability, this lone pair electron is making for an asymmetrical shape where you're going to have regions that are different than others. So the best answer here, look through the choices, they're the same. The molecular geometry and polarity are the same. No, because the molecular formulas are similar. No. The same because they're not the same. Are different because the lone pair electrons on the S, yes, makes it negative end of the dipole. Well, that is something that people could pick, but we do know that oxygen is a little more electronegative, being that it's an N equals 2 atom. It's smaller, okay, so it's going to be more negative. So the actual negative end would be where these O's are in the bent molecule. So C is not the good choice here. The best choice is D because different. They're going to be different just like C was because S has a greater number of electron domains, right? Domains are how many regions of space where bonds are. 1 for the lone pair, 2, 3, all right? and that surround the C. And having that many domains creates the shape necessary to create this imbalance of charge. So we're going to have the sulfur, okay, pushing this downward into an asymmetrical type of scenario where we're going to have negativity here and less negativity here, which is going to be the positive. So D is the best answer. Number 24. Okay, so number 24, consider the mechanism for the reaction above. And we have this reaction here, and we have this mechanism. All right. And we're considering it for this reaction. Which of the following must be true? And of course, I'm going to start again. All right, so in 24, we have this reaction. And this is the mechanism for the reaction. This is the series of steps. And each of these single steps is an elementary step. All right, and the complete bunch of steps is called the mechanism. So if this, in fact, is the mechanism for this, that means it takes 2 steps to make this. Which of the following statements is true? Step 1 represents a unimolecular reaction, and that is not right. Unimolecular means you have one element by itself as a reactant. Well, we really have two NOs. So step 1 represents really what we call a bimolecular, so that doesn't make sense. Increasing the concentration of NO will decrease the overall rate of reaction. Well, generally speaking, if you increase the amount of reactants, they're going to collide more often. When they do so, the reaction rate will increase. So changing the concentration or increasing the concentration, okay, will increase your rate, because generally speaking, your rate law is R is equal to K times the concentrations to some orders. And if you increase the concentration, the rate increases. Now, there are some very small examples of having orders that could be inverse relationships, but that's not what we have here based on this mechanism, as we'll get into in a second. So that doesn't make any sense. Raising the temperature will change the value of K, and it will change the rate. So it will have an effect. Temperatures make reactions go faster because they will collide, make collisions happen. There's more kinetic energy in the reaction vessel, but clearly this K is temperature sensitive, and that will change the rate. So that doesn't make any sense. And so that leaves me with D. The rate law is consistent with the mechanism, and by process of elimination, that's the answer. But I want to make sure that we understand what this is for any part 2 question. So how could I come up with this rate? Well, let's look at the step 1 here. If you notice, this is an intermediate. If we know the slowest step is the rate determining step, okay, we know the rate law comes from this exact elementary step. We have an issue here. The issue is that I have an intermediate. It's something that links one step to another. And it's my issues because my rate law cannot have an intermediate in it or a catalyst. So I'm going to have to find a way to get rid of this intermediate and try to find some equivalence for it. So I know my rate law is based on the second step, and this is an elementary single step, so I should be able to write rate law, or R, is equal to the K, okay, times N2O2 to 1 power, because there's a coefficient here, times O2 for the first power, because there's a coefficient here. And only when we know the single step, and we do so because it's slow here, can we make the coefficients become the exponents. But like I said, this is an issue. I can't use this. I'm going to have to relate that value of the concentration of the intermediate with the other fast reversible step. Now, the fast reversible step means that as fast as this reaction goes back and forth, that means that NO2 makes this unstable intermediate and it immediately jumps back. So this goes here, this jumps back. But there might be an instance where O2 can hit this N2O2. There might be that small time where just by luck an O2 hits there. This is the slowest step because O2 has to wait for N2O2 to be basically around long enough to hit it. So this is a fast reversible. This N2O2 breaks down too fast. So step 2 is essentially waiting for N2O2 to be around long enough by chance so that O2 can hit it, because normally it goes backward. So as fast as N2 is made, okay, so we can relate the rate of the appearance of N2O2 with the forward reaction, because the forward reaction produces it as fast as it breaks down. So there's a link here. The availability of N2O2 is equal to the forward rate equals the reverse rate. So the availability of the N2O2 is linked to this equilibrium reaction. So what I'm going to do is take step one. I'm going to do the rate of the forward of step one, and that's equal to K of the forward step one. I'm going to take that elementary step, which is NO, to the second power, and it's equal to the rate of the reverse, which would be K of the reverse of the first step, and that would be that would be N2O2, the intermediate, to the first power, because there's a 1 there. And now I'm going to solve for this. So the concentration of N2O2, that's the intermediate, is equal to, well, K of F1. Let's go back here. Let's make that blue to make things nicey nice. This is K. This is K of F1. Already has an NO2 squared in it. I'm going to divide by the K of R1. I'm just solving for the concentration. K of R1. And so I've got this new value of K here. And this is important, very important. At this point, what I have is I've got some kind of equivalence, or I've got what N2O2 equals in terms of a reactant that can go into my K. So this is equal to all of this, and I'm going to put that in here. Okay, so that's going to go right in here. So where this goes is this. So I'm going to put my N2O2, NO2 I should say, squared, and then I have my Kf of 1 over my Kr of 1, and essentially, as you can figure out, the K of the second step plus these two guys in this fraction equals to the K of the reaction, and now I have what? NO2 squared, O2 to the 1, and if you notice, it's exactly what the reaction here is. Now, you didn't have to do all of that to answer the question. You could just eliminate the bad choices, but the reason I just did this here is so that you can see this when it's a part 2 question. And all I did in a fast equilibrium is relate, okay, the intermediate, which cannot go into your rate law, with one of the original reactants by the idea that the reactant is becoming the product as fast as the product becomes the reactant. So therefore, the availability of this intermediate is related to the availability of NO, which is a reactant. So hopefully you followed some of that, and that's how we do that in a part 2 scenario. Okay, so number 25, the diagram above shows molecules of bromide and iodine drawn to the same scale, which means iodine is bigger. It's a bigger atom. It's in a row that's lower, okay? N equals 5, okay? N equals 4. I know we don't use quantum numbers, but it's really to understand that the size of the atom is indexed by the period number. Any case, all right, so which of the following is the best explanation for the difference in the boiling points of liquid bromide and iodine? Okay, so iodine is 184 degrees Celsius, and bromide is 59 degrees Celsius. Okay, well, clearly with a higher boiling point, that means that there is greater intermolecular forces of attraction. Boy, we have seen this before in the same test. They are really hammering this concept, stronger attractive forces. So the question is, why would this one have a greater force of attraction? Okay, now they're trying to make you look at the size of the radius maybe as a distractor in this question. Look at the choices. Solid iodine is a network solid, network covalent compound. Network compounds are covalent compounds that continually make covalent bonds in all directions. We talked about graphite or diamond that has that, diamond anyway, has that continuous sp3 hybrid structure, that tetrahedral that just keeps going in all directions, whereas the graphite would be that sp2 structure. But no, this is just a molecule, and if we're going to separate other molecules, then it would not have, they wouldn't. Okay, so iodine is basically molecules that attract each other, and iodine we know to be a solid compound. It does so because it has pretty strong attractive forces between the two. Again, it's iodine bonded to iodine. Okay, if you look at the Lewis dot structure, iodine has 7, so it makes this kind of a compound that they'll draw this way. But it's really, again, it's the attractive forces between the iodine molecule that determines its boiling point. In the case of a network solid, you'd be breaking bonds, and that's why network solids have tremendously high melting points, okay, and boiling points, which these are clearly not. Okay, so we get rid of that idea right away. The covalent bonds in I2 are weaker, okay, than we are. Well, we're not talking about bonds. Again, boiling points are not about breaking bonds. They're about breaking intermolecular forces of attraction. How do these molecules stick together? That's what this is about. Do not confuse bonds with attractive forces. So that is something you want to stay away from if you're talking about explaining in a part 2 somewhere in a free response that talks about why something has a higher boiling point than another. Do not talk about the breaking of bonds. It's about breaking of the attractive forces, the intermolecular forces of attraction. Okay, so now we're down to something either C and D. Bromide has a greater electronegativity. It does, okay, but that would mean that bromide's attracting electrons greater, and because these are non-polar bonds, bromide and bromide, I should say, then it's really going to have no bearing on this whatsoever. Okay, it's about, again, the attractive forces. So D is gone, and again, by another process of elimination, we have C as the answer. And the answer is that iodine has stronger what? London dispersion forces. Why? It's got a greater and a larger cloud of electrons than bromide has. Being in row 5, okay, and having a higher atomic number, it has a greater number of electrons. So it's really about that iodine is more polarizable. It's got more electrons, and more electrons can actually shift to one side or the other and create this momentary dipole. Okay, so it's about the strength of the intermolecular forces, more polarizable, therefore higher LDF forces, and that's what this answer is about, and we're talking about 25 is C. Okay, so number 26. Okay, we've got some more gases in containers. I'll tell you, the AP loves gases in containers. So in this problem, they're giving their famous bunch of gases in containers, and they're giving me a hint here that argon is 2.0 atmospheres for 1 liter. And since we have all 1 liter containers, I can do a comparative amount of moles. Since this is 2 atmospheres and this is half as much, this must be 1 atmosphere of pressure because I have half the particles, then half the collisions. Remember, when molecules move, they collide. And when they collide, they cause pressure. And these boxes here have half the pressure. Now, in this question, they tell you that the ratio of the number of the atoms in here is a 2 to 1 to 6, if you didn't want to count. So I know that this has half the number of moles of particles because they tell me that right in the problem. Okay, so 2 to 1 to 6. So if 6 is 3 times the number of 2, then if I was to count, and I guess I will, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 12 particles. There's 4 here. There's 3 times the number. So if you think about it, the number of atoms here is 3 times this number. 3 times 2, it gives me an atmosphere of 6. So we have 2 atmospheres of pressure to 1 atmosphere of pressure to 6 atmospheres of pressure. Okay, Now they're going to stuff all these gases into this box here, which is twice the volume. Now don't get confused because you say twice the volume of individual box. See, this gas feels 1 liter, okay, of volume. When I put it in this box, this gas, which are really, really small, is going to feel the volume of 2 liters. This gas, which is now in 1 liter, will fill the volume of 2 liters. See, these gases won't really get in their own way, won't get in each other gas's way because they're infinitely small, even though they draw them pretty big in these diagrams. So each of these gases is going to feel like they're in 2 liters. So what's happening is the volume is going to increase, or times by 2, and the pressure, okay, is going to decrease by 2. That's Boyle's law, right? Pressure is going to decrease when the volume increases. And so the volume is increasing 2 times, the pressure decreases 2 times. So essentially, this is going to go to, let's change the color, from 2, okay, well, the number of compounds, or number of particles stay the same, so I should do it up here. Should go from 2 atmospheres to 1 atm. And this is going to go from 1 atm to 0.5 atm. And this is going to go from 6 to 3 atm. When all of these are placed in this box. Okay, so you add them together, and 3 plus 0.5 plus 1 is going to give you 4.5 atmospheres. And why does that work? Dalton's law of partial pressure states that the individual partial pressures equal the total pressure. Okay, the little trick to this was that we had to recognize the fact that the pressure of this gas would subsequently give me the pressures of each of the gas, now that I know that 4 particles equals 2 atmospheres in this volume. And then I had to realize that if I double the volume of the space for each of the gases will feel as if the volume doubles for each of it, since these gases don't really get in their way. So that means that I would have the what? Pressure for each as the volume doubles. Boyle's law. All right, so 26 is B. In number 27, they say the dissolution of an ionic solute. Fancy word for just dissolving, okay? So I'm just going to write it here so we don't get intimidated by that word. We're just dissolving. Dissolution of an ionic solid in a polar solvent. Well, it has to be polar because ionic compounds are positive and negative. So this could be the positive, this could be the negative. Okay, now it can be imagined as occurring in 3 steps. All right, so what they want in this question is they want you to figure out which of the best describes the enthalpy change for each step. Okay, so we have to look at each step. Now in these 3 steps of dissolution or dissolving, the first step they're talking about is taking the ionic solid, okay, the salt in this case, and breaking it up into its individual particles, the plus and the negative. Okay, so that's all we're doing here. And of course it takes energy to do so because we have positive ions attracting to negative ions. So we're going to have to break the ionic bonds, and anytime we break bonds, it takes energy. So delta H has to be positive here. It takes energy to break bonds. We are breaking bonds, and bonds, even if they're ionic, are stable states. And if we're going to break a bond with a very, very stable state, right, low energy, okay, then of course it's going to take a lot more energy to break the bond, and that's what would be right there. So breaking the bonds, delta H is definitely positive in this case, okay? Takes energy to break that attraction. All right, now let's do step 2, where we have water molecules attracting each other by this hydrogen bonding, by this electron deficient H's, as we've talked about before in other problems. These are not actually covalent bonds, these are attractive forces. However, just like breaking the ionic attractions or bonds, and some people do consider ionic attractions, but we're considering them bonds here, in order for water to make openings so that the salt can fit in there, and of course it doesn't do that by itself, Okay, kind of these steps are mixed together, but they're just breaking it up. For water to be broken apart to do so, to create openings, you would also need energy, and delta H would be positive because it takes energy, same thing, delta H is positive again, it takes energy to separate water molecules. So if I've got to move this one, okay, this water molecule somewhere to create an opening over here, then it would take energy to overcome this attractive force because water is in this scenario because it's stable. These attractive forces stabilize the water, and things that are stable, like over here, low energy, take energy to break. So you have to understand that these are both endothermic. Okay, we're pulling things apart. We're breaking either attractions, okay, or in this case, bonds. Now, in this final step, where we put the salt ions, okay, right into these spaces, okay, well, now we're creating new attractions. New attractions. We're creating these molecule ion attractions, and because we're creating a new attraction, and because water having a negative end and a positive end, it can interact with these positive or negative ions accordingly. So we're creating new attractions, and attractions are more stable than without any attractions. Okay, so these new attractions that we're creating, and sometimes you guys drew them last year as if this is a positive ion and you have the negative end of the water surrounding them, we would have these types of attractive forces. And again, the bottom line is that if the salt is going to dissolve, it does so because it makes some sort of a stable arrangement with water. And what's creating stability is these new attractions. Water now is attracted in some fashion to these ions, and it gives it some stability. And that's the reason why the boiling point is going to be higher now in this area, because of the increased stability you've given it. It's harder for water to overcome these attractions and escape and produce vapor pressure. So this position here, where we go to moving from these free ions or water that's been moved over to new attractions, delta H has to be negative and exothermic because we're creating a new stable state, okay, a new low energy state. All right, so all three steps are exo and endo? No way. All three steps are endothermic? No. Step 1 and step 2 are endothermic, and the final step is exothermic. Okay, so D is your answer, creating, and you should know, anytime you what? Break bonds, okay, it requires, or attractions, delta H's are always going to be positive. If you notice the bond energies that we used in this course, if I was to give you bond energies, all bond energies are positive. The energy to break, let's say, a H to H bond, I don't know what that number is, but it would be some positive number of kilojoules. There is no negative energy needed. You would need to add energy to break this stable process. Okay, moving forward. Okay, number 28, a student mixes dilute silver nitrate with excess sodium chloride to form silver chloride. Gosh, how many times have we seen this precipitation reaction? Okay, so another particulate type of illustration question. They love these. Okay, which of the diagrams below best represent the ions that are present in significant concentrations, okay, in the solution? All right, so I look at these and I say, okay, I've added excess sodium chloride. Excess, that's important. Okay, now sodium chloride, as we can see and notice, is going to dissociate into sodium plus and chloride negatives. So there's no sodium in the overall process, so it's a spectator. But since it's an excess chemical, we could expect to see a lot of sodiums, more so than anybody. Now, of course, we produce the same amount of chlorines, but what's that going to do? That's going to react with the silver ions and make silver chloride. Look at the KSP, it's tiny. That means the silver chloride, the reactant, is favored. Now, what I will say is they wrote this reaction this way, but KSP, careful, is always based on writing solution equilibrium this way. So I'm just going, for my own intents and purposes, going to write the reaction like this so that my KSP reflects that. It probably makes no difference in the question, but it's a good idea because you can write these reactions any you want. But when you say KSP, we want to talk about the product of the ions okay, and the ions would have to be my products to make sense of what the KSP represents. So that's why we write it like that. But bottom line is, okay, I am adding excess sodium chloride, which means I'm adding more sodium and chlorine than I have silver. However, okay, as long as I match, there's going to be some amount of chlorine that matches with the silver. So this chlorine will take out all the silver if I add excess, right? More sodium chloride than silver plus. So I should not see any silver in my drawings. You notice I have some silver chloride, but I have some silver ions. Silver ions in chlorine won't exist like this. If the KSP is 1.8 times 10 to the negative 10, there's no way that that can exist like that. Most of the Q is going to be so tiny, okay, or for that Q to be smaller than K to have some these ions present. So you're not going to see any of this present. So that means that this doesn't make any sense. And for the same reason, I can get rid of choice D, because again, I've got some silver ions and chlorine ions sitting there undissociated, okay, or I'm sorry, dissociated and separated, when in fact they'll make a precipitate based on that very small equilibrium KSP. So I'm left with these two choices, A and C. Now if I look at A, I've got a lot of nitrate, and that makes sense because I added silver nitrate. Okay, that's going to break apart into silver plus. As we just talked about, the silver plus is going to hook up with the chlorine and leave you with the spectator nitrate that doesn't do anything. But if I look, I see I have 1, 2, 3, 4 nitrates, and I have 1, 2, 3, 4 sodiums. Well, we added excess sodium chloride, which means we added more sodium chloride than there was silver nitrate. So there should be more sodiums, right? And of course, there's the same number of sodiums. So this would be what it would look like if I just added just enough sodium or sodium chloride to what? Precipitate out all of the silver ions. But I added excess, so there should be more NaCl's than nitrates. The nitrates, of course, come from the silver nitrate, and of course, Na plus comes from the sodium chloride that I added. All right, so it should be clear that this number has to be in bigger quantities, and it's equal. So I, again, get rid of it, process elimination. C has to be the answer. And if you see, there's no silvers floating around because you notice, well, they're all going to be locked up into this crystal. Notice there's extra chlorines. Why? Because we have extra sodium chloride. All right, not only going to we have sodium ions hanging around, we have extra chloride ions. And notice there's more sodium ions than chlorine ions. That's a great little hint there too. And the reason for that is because, well, the sodium is always going to be a spectator, but some of the chlorines had to react with some of the what? Silvers. So the chlorines will have to be in lower quantity. Because we added excess, there's going to be some chlorides that are hanging out there that go beyond the number of silver ions available. So that makes sense. And notice we have some nitrates there because, of course, that's just hanging out. So this makes the best sense of the diagram. So number C. Okay, so this next question, and we'll do number 29, is we have, guess what? Some more gases in a container. And it's in equilibrium, at least the reaction shows here. But in any case, the PCl5 decomposes into two other compounds. And what they said, a pure sample of PCl is placed in a rigid, evacuated 1 liter container. And the original concentration is 1 atmosphere. Okay. The initial pressure is 1 atmosphere, and the temperature is held constant. It reaches equilibrium with its decomposition products as it decomposes, and you notice the pressure increased. So what happened? Why did the pressure increase once it started decomposing? Okay, one molecule breaks apart into two more molecules. So one breaks apart into two, and because these are gases and fly around the container and collide with the sides of the container, you're creating more molecules of gas, and that is why the pressure increases. So even though, you know, we say there's a minus X and a plus X here, in terms of how much is going away from the initial conditions, we are overall going to increase the number of overall compounds. Yes, some of the PCl is going to go down, but for every one that goes down, you produce two. So there's going to be an increase in the total number of particles, and the more gas particles you have, the greater number of collisions. So knowing that the pressure overall increased from 1 is telling me that we've created an overall number of greater atoms. If I'm in a fixed volume container and the pressure went up, it only does so if there's more moles of gas. So pressure equals PV equals nRT over V. And if you increase the number of moles N, you increase the pressure, keeping volume constant and temperature constant. Absolutely. So the answer clearly is, all right, which of the following is most likely cause for the increase in pressure? Okay, now, as you increase the number of molecules, the frequency of the collisions with the container walls increases. So obviously 29 is C. Okay, number 30. As the reaction proceeds toward equilibrium, the rate of the forward reaction. Now don't confuse rate with delta G, okay? But we do know this. We do know that if we plot the concentration of my reactant, okay, which is PCl5, just call it reactant, we know that it's going to drop and then level out, okay, as it reaches what? Equilibrium. The rate of the forward equals the rate of the reverse. And you may say, well, why does it drop? Well, it drops because as we go forward, the amount of the concentration of the reactants goes down. So there's less of these, so they collide with themselves less often, and therefore the rate drops. Okay, and as you talk about, rate is equal to the rate law constant times the concentration of our what? Reactant. And I know this is usually initial concentrations, but as the concentration drops, okay, the rate has to drop, no matter what order it is. Okay, so we would say it's going to decrease, and it's not going to become zero. Zero would imply that at equilibrium, that you stop going, you stop working. It looks like nothing is happening. We know at equilibrium, the amount of these combinations or these reactant and these products are equal because the rate of the forward equals the rate of the reverse. So the amount of reactants and products stay constant. So it's going to drop down until the reverse reaction picks up enough to equalize it going in the forward. So we would say that it decreases. It does not become zero, though, because there is still a forward and reverse going. Equilibrium is pretty boring. Looks like nothing is going on, but we do know reactants and products are changing sides, and that's why the amount of these stay constant, but there's something called dynamic equilibrium where they actually keep going. So it doesn't go down to zero because there's still movements back and forth. They're just going at equal rates. Okay, so that's 30. Now 31, if the decomposition reaction would go to completion, the total pressure in the container would be what? Well, if we're going to go to completion, what do we have here? Well, we said the container is not going to change, and we have how much of the initial pressure? Well, we have 1 atmosphere. Okay, 1 atmosphere of pressure for my initial reactant. And what do we know? We know that this is going to be 1, 0, 0, and it's going to go to completion, which means it's going to be minus, okay, the entire pressure. And my 2 reactants would be plus 1 atmosphere and then plus 1 atmosphere. Okay, so if you notice, we're going to get rid of, and I can just put this in to make sense for those that don't know, what am I doing? Well, what I'm doing is I'm taking PCl5, and with this double arrow, making PCl3 plus our chlorine. And what we're having here is we have the initial amount, that's our I, and there's 0 amount here. What's the change is it's minus 1.0. Why minus? Because it's going to go to what? Completion means it goes in one way until it runs out. So the change is minus everything. This goes to 0. That's the completion part. These guys started out with 0, but now they've what? This is minus 1.0. This is plus, and now we have 1.00 pressure and another 1.00, and their atmospheres, And we know that pressure with gases is proportionate to moles. So I can use this Stoich table in pressure. So I'm left with what? I'm left with two gases that each have 1 atmosphere apiece in the same container. So I have 2 atmospheres. 1 plus 1 is 2 in this case. Can you imagine? 1 plus 1 is 2 for an AP question. Crazy. Okay, 32. Okay, so continuing on with the same group of questions for this reaction above, they said at equilibrium we have 1.40 atmospheres. We started with 1 atmosphere of the individual gas before it decomposed, and then it went to 1.4. So clearly it went forward. The question is, can we figure out what the value in terms of the equilibrium constant is? Well, we know that Kp, we call it Kp only because it's dealing with equilibrium of gases. So that would be, products, it'd be PCl3, okay, times Cl2 over PCl5, okay? And now, okay, so we know that we went forward a little bit, okay? And now we might expect that, hey, we made some products and there's more products than reactants, it's greater than 1. But you really got to think about this sometimes, because you're multiplying 2 of these to 1. It's not always going to be as clear as that. I know I always say the more products you have favoring the products, it's greater than 1, and if we're moving toward the reactants, but how much is it favoring? Is it totally favoring? Okay, well, let's understand this. If we had initially 1, and let's just we're going to put it like over here, we had 1 atmosphere of pressure, and we had 0 for the PCl3 and Cl. For us to get a 1.4, okay, we must have lost minus 0.4, and that gives me a plus 0.4. I'm just showing you how this can swing in ways that you may not have thought. Plus 0.4 for these guys right here. So what do I have? Okay, well, I have 0.6 left, okay, and then positive 0.4 and positive 0.4, and that's one way to think about how we get the 1.4. Now, you don't have to do quite this math to figure that out. That's not necessary, but I want you to realize if we went to 1.4, then that must mean that we didn't completely favor everything, but there are some products being made. So you plug these numbers in, you'll see what's left is 0.6 on the bottom, and I'm using atmospheres because it's a Kp, and I really should use parentheses here if I'm using Kp, but that's just being polite. And of course I would have 0.4 times 0.4, which is 0.4 squared. Okay, and if you think about the math, 0.4 is 0.16 over 0.6, and this is going to be a what? This is going to be a smaller number over this bigger number, so K is clearly going to be less than 1. And I guess you could still think that the reactants are still a lot favored because we still have what? A lot more of the reactants than products. But it's not always as clear, okay, sometimes. So sometimes working out the numbers can clarify that. So B is the best answer. Reactants are still favored if we went to 1.4 because this number would be a 0.6. And some people can see that right away. I can't. Sometimes I have to just work out the math a little bit to make sense of this. And you don't have to. You can see that clearly 1 to 1.4, you still have a lot of reactants, but it's not as far apart as you may think. Okay, so next question, number 33. Additional chlorine is ejected into the system at equilibrium. Okay, well, if additional chlorine is being injected, it's going to be a big spike. So I'm looking at basically between C and B already. It's not going to do that. Now, if we have something at equilibrium, if we're basically adding more chlorine to this reaction at equilibrium, there already is some chlorine there. By the fact that it's equilibrium, we have a forward rate and a reverse rate. There is going to be some chlorine going back and forth, so we're not going to start from 0 for another reason to get rid of that. Okay, now the question is, okay, what happens when I inject? Well, by Le Chatelier's principle, if I increase more of Cl2, we're going to add more, we're going to have more products than we're supposed to. And as I love to keep drawing, okay, if we have more products, the Q is now greater than the K, and the reaction is going to be more spontaneous in the reverse. So we're going to have an initial spike of Cl2, but then we're going to drop down. The question is, how much do we drop down? Are we going to drop down lower than we initially had? No, actually you're going to drop down, but you're actually going to have a little bit more than you had. And the reason for that is you're injecting more Cl2, so everything else has to readjust to a new kind of an equilibrium position to equal to what the value of Kp is. You're not going to drop down to lower. You're initially going to drop down, but not going to go lower from initial standards. If you were here, okay, you can't be lower than you initially were if you're going to inject more atoms into the system. Okay, so it makes sense that we go down from that spike, but not down as low. Again, the reasoning very simple is I'm adding more Cl2, more of this to the system. Yes, we're going to make it shift, but it can never readjust to its original position because I've added more atoms into the into the reaction container. So all the values are going to go up a little bit. They'll be in the same ratios essentially to give me the same Kp, but I'm adding to a sealed container. It has to go up a little bit. Okay, so that's why B is the answer.